So, we did Rg for viscosity in the last class, right, for the shell model, but there is one missing piece. So, what about the coupling constant? Coupling constant is a prefactor for the nonlinear term, right. That is what we did for phi 4 theory. So, for phi 4 theory we had lambda phi 4, right, in the Lagrangian, and the m squared phi squared, right, and then of course, there is a gradient which becomes k squared gradient that phi o squared, right. So, we renormalized m squared, this was not renormalized, but lambda was also renormalized. Now, we want to know whether lambda for what happens to lambda for the shell model, right. This is an interesting question. It turns out lambda for the shell model, let me just first show you what is this lambda. So, this renormalizing the coupling constant for shell model. So, this is the nonlinear term, everybody agrees with that. So, there is a factor in front lambda, like lambda phi 4, similarly we have lambda into nonlinear term. Now, it is possible that lambda will also change with under Rg when I rescale, there is no guarantee that lambda should not change, but it turns out there is a symmetry argument. In fact, there is a Galilean symmetry for Navier-Stokes equation, and based on the symmetry arguments you can claim that lambda should not change under Rg. It is not easy to well, it is not according to me it is not possible to show for the shell model directly, but shell model is supposed to represent Navier-Stokes equation in turbulent regime. So, we will say well, for Navier-Stokes equation lambda is unchanged. So, for the shell model also lambda will be unchanged, that is the argument I am going to make. So, we want to know whether lambda, what happens to lambda. Okay. So, as I said, the proof is that Galilean invariance, which I am going to describe in a minute, implies that lambda is unchanged. Lambda, in fact, lambda should be equal to 1 including Rg. So, let us look at the proof, which is pretty simple. So, this is a Navier-Stokes equation, right. So, this is the partial d by dt du by dt, and this is a nonlinear term u dot grad u, but I put a factor in front lambda which is 1 at the onset, but we see whether it becomes different than 1 under Rg, and this is grad p and this is a viscous term. Now, what is the Galilean invariance? So, the equation, well, basically the idea is that the laws of physics do not change when I go to a moving frame or stay in the lab frame. Laws of physics are the same, laws are the same. Okay. So, there is a lab frame which you denote by x. X is a real space coordinate and time is time coordinate. But when I go to a moving frame, then my coordinate system is, so of course, you say x, y, z, t, okay, the four coordinates, 3 space and 1 time, but I am right now expressing only x. So, in the moving frame the coordinates are x prime t prime, okay, but Galilean invariance you know that t equal to t prime, no, the time does not change. Lagrange invariance, of course, t goes to gamma t prime minus x v, but we are doing Galilean invariance which is good for non-relativistic flows. So, what is the relation between the two? So, this is the moving frame is moving with velocity u naught along x direction, we will assume that. Okay. So, that is my mean speed. Now, we want the equation to remain unchanged. So, equation should be same when I replace u by u prime, grad by grad prime, t by t prime. Is that clear? So, we know this transformation, I mean, so I will not go one by one. For example, x equal to x prime plus u naught t, right, t prime, you might have seen this. Velocity u equal to u prime plus u naught, which is x, right. So, velocity in the lab frame is more, so relative velocity will get added up. So, these are very standard. Time derivative and space derivative are slightly involved, but that is also doable. We just do standard partial derivative formulas, then you will get these transformations. So, as I said, x is that, t remains unchanged, but space derivative the partial derivative like t goes like that. Okay. This you can easily show d by dt of any variable phi is d by dt prime. So, we write d by dt prime phi dt prime by dt plus d phi by dx prime dx prime by dt, right. So, that is how we will get this this stuff. Okay. So, dx prime by dt will give you u naught, clear. I mean that is how we just use the standard mathematics formulas to derive this relations. Okay. And the velocity transforms that way, and pressure is unchanged. Okay. Pressure is coming from the divergence of velocity, and divergence nonlinear term is unchanged. Okay. So, we substitute them in terms of u, you put u prime, for t you put all that. So, this is what we get. Okay. I am avoiding the algebra, okay. It is boring for you and boring for me as well. So, we just replace u by u prime plus u naught t. So, this is part. So, dt prime. So, I just plug it in. Okay. So, here velocity field is replaced by u naught x hat plus u prime, and then we have divergence, and of course, I have u naught added, but u naught is a constant. So, Laplacian prime is gone. Okay. So, what are we getting here? So, we are basically, this is the equation I get for the prime variable, everything is in primed. Okay. Of course, u naught is a parameter. Okay. Now, does it look like original equation? As I said, we should look like the original equation, that will be the invariance, right. That when you say laws of physics is unchanged when I use u variable or u prime variable, but they do not look the same, right. I mean, I should get same equation. So, I expect this to be lambda u prime dot grad prime u prime. Okay. So, this is looking good, but this term is a new term and this is a new term. Pressure is same as before, viscous term is same as before, this is same as before with u changed by u prime, but these two terms are a problem, right, these two terms. So, one way is to cancel the two terms, one is coming with so one term is lambda u naught. So, this x hat dot grad will give you d by dx, right, dx prime u prime, this is this term. Now, what about this term? So, these are exactly looking same form, except lambda is sitting there. So, what will cancel it? We have set lambda equal to 1. If we set lambda equal to 1, this will cancel with that. So, this shows that if I want to impose Galilean invariance, then lambda must be equal to 1. Okay. Now, this is at for all scales, but I derive Navier-Stokes equation at a coarse grained level that should also be symmetric under Galilean invariance. That means, this derivation is to be applicable at all coarse grained levels. So, that means lambda must be equal to 1 at all levels. Okay. So, lambda is not renormalized, okay, under coarse graining. So, d lambda by d L, L was at b equal to e to power L, right, that is the thing, is 0. So, the beta function is in fact is 0 for this. Okay. It is interesting proof, but this, well, I mean, this is straightforward. Now, of course, I did not prove it for the shell model, but shell model, as I said, is basically a model for the Navier-Stokes equation. So, we expect the nonlinear term for the shell model too should be respecting this property. So, lambda is unchanged even for the shell model. So, Galilean invariance is a very important symmetry, which immediately tells you that lambda is unchanged, and actually, so basically shell model is not in real space. So, I cannot apply this argument, okay. But as I said, similar physics as NS equation. So, lambda is not renormalized for shell model too. So, please keep in mind that nu was changed, and this nu goes as k minus 4/3 is function of k, and this is exactly what we get for the Taylor diffusion. So, viscosity in fact increases as length. with length. So, bigger the eddy is, bigger the diffusion, and this is a coming from theory. So, interestingly we are able to derive this using RG theory.